Hi there, this is a video on how to name and write formulae for ionic substances. This ties in with the Unit 4 of the IB, particularly 4.1, which is all about how you sort of predict name formulae for ionic substances. Hopefully this video will be helpful. I find it's a difficult thing to do for students to work out the formulae for ionic substances, particularly if they're dealing with polyatomic ions and transition metals. And there's also a lot of difficulty working out the names. So hopefully this tutorial will help you. It will be helpful for people doing the IB, maybe people in grade 10, or if you're in year 11 of GCSE, or even if you're doing A-level. Hopefully this video will be useful. So, let's get started. So before I go anywhere, I'd like to just talk about the particular IB focus that it is. It's under the application and skills of 4.1, and the particular statement that you have to be good at is the deduction of the formula and name of an ionic compound from its component ions, including polyatomic ions, and that includes knowing what the polyatomics are, and we'll cover that a little bit later. So before I go any further, just go through a couple of basics. I'm not going to go into massive detail about this, but I'm just going to bring out the basics just to remind you. So ionic bonding happens between metals and non-metals. The metal will lose electrons to become what we call the cation. The one exception of something that's a cation that's not a metal is the ammonium ion, which is NH4+. Likewise, the non-metal will gain those electrons that have been lost and they form anions. And these ions are kept together by what we call an electrostatic force, which is effectively the attraction between positive and negative. And that is the ionic bond. So, how do you name these metal ions when they form these ionic substances? Well, let's look at group 1 and 2 first for metal ions. Group 1 and 2 is shown here on the right. Now these will always have a +1 or a +2 charge, and it depends on what group they're in. If it's in group 1 it's +1, if it's in group 2 it's +2, and it's related to the number of electrons they have to lose in order to have a full empty shell. So let's take sodium as an example. So sodium is a popular one. So just changing the colour. Okay, so here's sodium, which is just Na. Now if I lose an electron, it's going to form Na+. You can write E- if you like as well. This is the sodium ion. Now you don't have to change anything on the name. It still remains sodium ion. So I'm just going to write sodium, and I'll write ion. Okay? It's quite important when you do the ion bit. It becomes less important when you do the equations and the naming, but for other answers you always want to say sodium ion. Let's take another example. Let's do strontium. So strontium is Sr. Just write strontium. Now if I ionize it, I have to get rid of 2 electrons. So it has to be Sr2 plus 2 minus. Again, I don't have to change the name, it's always the same. So it's going to be strontium ion. And again, this can be dropped when you're actually doing the naming, which we'll do later. So when they turn into ions, the name does not change. Now that's slightly different with transition metals. Now with transition metals, they can have a range of different charges. When you do redox later on, they're called oxidation numbers or oxidation states. This is the D block, which contains all of the transition metals, and they can have different charges, as I said. Now, as an example, let's take titanium. If you've got titanium and you ionize it, let's say to 2+, right? It would be titanium to begin with. And then when you ionize it, it would also be titanium. Just put the 2 minus there. But because you've ionized it and removed 2 electrons, I have to represent that by Roman numerals. Now, if you're not familiar with your Roman numerals, 1 is that, 2 is 2 of those, 3 is 3 of those. To do 4, it's that with a V. V represents 5 in Roman numerals. And 5 is V, 6 is that with a stick, and 7 is that, and so on. Now this has got 2+, so I have to use 2, and I have to put that in brackets. Okay, and that's your ion. So Roman numerals are used for the charge they have in brackets. If I take another example, let's say titanium, instead of going to Ti+, 2+, let's say I went to Ti 4+. Okay. Again, it's still called titanium. But because it's 4+, I have to change the number in the Roman numeral. So it's titanium, and I have to put the 4 from here, so it'd be ion, that's your 4, ion. So you just have to be quite savvy with working out which Roman numeral is required for the ion you've got. So let's now name non-metal ions. Now non-metals are found in the P block, which is here. You can see there's not many of them. And you're probably going to have to deal with maybe group 7 mostly, group 6 pretty often, 5 rarely, and carbon very rarely comes up. I won't talk about hydrogen at the moment because that's a bit more complicated. Now when you're naming non-metal ions, you always have to replace the end of the name with the "-ide" suffix. As an example, let's take oxygen. Now oxygen is just O. Okay? In order for it to be happy, it needs to gain 2 electrons because it's in group 6. So it will then become O2 minus. And you can always write 2E minus plus O. And that will create O2 minus. Now in order to name this, I have to not put in this bit, and this gets replaced by the "-ide. So it becomes oxide. There's no fixed rule on what part of the name gets replaced. It's kind of, if it sounds right, then it works. And I'll show you a couple other examples in a moment. So that would be the oxide ion. Another example would be fluorine. So fluorine only needs 1 electron, so we do E minus plus F makes F minus. Cool. Just F minus. So this is fluorine. And now it's turned into an ion, so it's fluor, and I'm going to get rid of the "-ine" bit and make that "-ide." Okay. As you can see, they've got the same suffix, and it's a fluoride ion. So you can see that for oxygen it's "-egen", which was replaced. For fluorine it's the "-ione", which was replaced. So there's no fixed rule, as I say. It depends on what you've got. So for fluorine it becomes fluoride, oxygen becomes oxide, nitrogen becomes nitride, carbon becomes carbide. Alright? So you just have to sort of play around with it, and you get better with the naming as you do more of these questions. So, now let's look at polyatomics. Now polyatomics, there's no method for working out what it is, you just have to remember them. I'm going to go through the 7 which the IB requires you to understand and use for questions. They will not necessarily give you these, you do have to learn them. So the first one's NH4+. We talked about this before. It's one of the rare positive ions which is not a metal. This is what we call the ammonium ion. So it's related to ammonia, which has the formula NH3, but because it's gained a proton, it's gained a hydrogen atom, it becomes ammonium ion. Next one is OH-. This you may have come across before. This is the hydroxide ion. Then we've got NO3-, and this is the nitrate ion. Now this is an example of what we call an oxoanion. An oxoanion is an ion that contains oxygen, right? And it's polyatomic as well. So it's polyatomic and contains oxygen. So that's nitrate. Oxoanions always end in ATE. Well, they usually do. The ones that you come across will always end in ATE. If you've got CO3 2-, this is carbonate ion. Okay? Again, it ends in ATE to denote that it's got oxygen in it. We've then got this one. Now this is the same as what I've just shown you down here, but instead of carbonate, I've now got an extra hydrogen, so I can just add hydrogen at the front of the name, so it's hydrogen carbonate ion. I think the one error I've got there is it shouldn't be 2-, it's just minus. Forget that. Next one is SO4 2-. This is what we call the sulfate ion. Right? Again, you've got the A ion, or the H suffix. And finally, this one, you can guess what it is. It's got phosphorus, it's got oxygen, it's the phosphate ion. Now remember, you have to learn these off by heart. That can be quite a laborious process. But the one thing I will say is once you do more of these questions and you practice it and it becomes second nature, these you remember off the top of your head, it'll be easy. But you have to practice, it doesn't come naturally. So how do you deduce formulae from ions? Well, in order to work out the formulae, we have to remember a couple of key things. The first thing is that ionic substances always have a neutral charge. So the number of positives always has to be balanced out by the number of negatives. And I think when you're starting out doing this, it's quite useful to kind of draw out those positive and negative charges. Now sometimes they add up to 0 normally. So let's have a look at Na and Cl. So for example, here's sodium, and it's plus, and it's Cl and minus. Now this only has 1 positive charge. This has 1 negative charge. You can see there's a 1-to-1 ratio. They naturally balance out. So as a result, the formula is NaCl. This gets a bit more complicated if they don't balance out normally. As a result, you have to use a technique which I like to call crisscross. And as an example, we'll do it with this compound. So here we've got potassium, which is K+, and we've got nitrogen, which is 3-. Now let's think about it. One potassium has a 1+ charge. These 3 nitrogens, well this one nitrogen I should say, has a 3- charge, which looks like this. Now we can see that they don't balance out. I need 2 more plus charges here to counteract the negative charge here, so the whole thing adds up to 0. Now the only way I can do that is by adding more potassiums. So here's another, and here's another, and now it should work. So we've got 3 over here, and 3 over here. In terms of what the formula will be, let's draw it out. So it's going to be K something N something. I've got 3 potassiums, you can see 1, 2, 3. So that has to be K3. Nitrogen, I've only got 1 of them, but each one has 3 negative charge. If that can stay as a 1, I'm just going to leave it alone. So that's quite a nice way of doing it when you start off. As you get more confident, you'll find a technique which is very useful to do it, which is called crisscross. And I'll show you what that looks like. Again, I'm going to write out my ions, so K+ and N3-. If I do crisscross like this, you'll see that the numbers that I've crisscrossed either side will denote the subscript used for that element. For example, in potassium, the 3 has come down to be the subscript for potassium, so that is K3. For nitrogen, the 1 positive charge from potassium has come down, so that I can just leave. So the formula for this is K3N. Let's try another example. Al3 plus and O2 minus. Let's draw them out. Now for aluminium, for one of them it has 3 positive charges. This is 2 negative charges. If I add another aluminium, that will give me 6 in total. Now in order for oxygen to balance that out, it needs to have another 2 of them. Now I've got 6 on one side and 6 on the other. I needed 2 aluminiums to make that work. I needed 3 oxygens to make that work. So to write out the formula, it's Al 1, 2. And for oxygen, it's 1, 2, 3. It's Al2O3. You could also just do it with crisscross. So if I just do my crisscross without having to do the drawing out, for aluminium, my subscript should be 2. You can see that matches up, so that's good. My aluminium has got this 3 going down to the oxygen, so I need 3 oxygens. Again, that's good. So you can see the crisscross does the same thing as what we've done here, but just a lot quicker. So I'm going to use the crisscross technique from now on when I'm describing the answer to some problems. So let's have a look at NaNO3. Sodium is plus, NO3 is minus. If I do crisscross, you'll see that sodium only needs 1 because the NO3 only has 1 negative charge, so I can leave that as it is. My NO3, the positive charge from here, which is just a 1, comes from sodium down to be the subscript for NO3. So that is just NaNO3. And that works. Let's try some more complicated problems. Now we've got NaCO3. Now sodium plus and the carbonate ion is there. Doing crisscross looks like that. Now you can see, if I want to work out the number of sodiums, I look up here, it should be 2. So it's Na2. For the number of CO3, it depends on what came down from sodium, which is just 1. So I'm just going to leave it as it is, and that works. Let's try another one. NH4 plus and O2 minus. Okay, so I've got NH4 plus O2 minus. Now if you look at this, if I do the crisscross, let's work out for NH4 first of all. Oh, sorry, that's wrong. The 2 from here goes down here. So I need 2 lots of NH4. So I'm going to put 2 there at the moment. But how many oxygens do I need? There's only 1 from the positive charge coming down to it. So it only has to be 1, so I can leave it as it is. But there's a problem. This, as it stands, suggests I need 42 hydrogens, which is clearly nonsense. What I do need is 2 lots of NH4. So to make this formula work, I had to put brackets around it, and then that's fine. Some students sometimes get confused and they do this, they write 2NH4O. That's not right, because if you do that, what you're saying is that you've got 2 lots of the whole thing. That's not correct. Okay. Moving on. Mg2 plus and PO4 3 minus. So for this one, let's write Mg2 plus and PO4 3 minus. If I do my crisscross technique, I can see that for magnesium, I need 3, because you can see the 3 from the phosphate coming down, so it's 3 magnesium. For PO4, I need to look at the charge on the magnesium. There's a number 2. That will now be the subscript for PO4, so I put the 2 down. Again, we have the same problem as before. This is telling me that I need 42 lots of oxygen. To say it's only 2 lots of PO4 requires brackets, like so. Okay. And then it works, that's fine. Now, if you want to work out the formula from a name, my one big tip here is to work out the formula for the ions first. Okay. Now let's take an example, which is calcium chloride. I want to work out the formula for the ion. So if I look at calcium, calcium's in group 2. So it has to have a charge of 2+. So it'll be Ca2+. Chlorine's in group 7, which is always 1-, because it only needs to gain 1 electron to be happy, so it's just going to be minus. So that would be Cl-. Once you've established what they are, you can then do crisscross. So now I can do either side. If I look at calcium, I need 1 because the 1 negative charge comes down here, so I need 1 of those. For chlorine, the 2 from here comes across, so I need 2 of those. Alright. Let's try another example. Calcium carbonate. Again, calcium's in group 2. So it's got to be Ca2+. Carbonate is a bit different. It's one of the polyatomics you have to remember. Now, if you remember it correctly, it's CO3, 2-. I can then do crisscross, and it shows me that it's Ca2, CO3, 2. This is a problem, because what we're saying is we need 2 lots of each. But do we actually need 2 lots of each? If you think about it, at the very beginning, Ca's a 2+, had a 2 positive charge. The carbonate had a 2 negative charge. You can actually see that from the outset, from the beginning, they balance out. So I don't need to add any more either side in order to get the correct number. So what it actually is CaCO3, that's your calcium carbonate. This is a very, very common mistake if students know how to do crisscross but don't understand the process behind it. The understanding is here. So just be careful with that. That can come up quite a lot. Let's try another one, iron oxide. So iron oxide, now I've got the 2+, because it's a transition metal. So I know it's going to have to be Fe2+. Oxygen, as we know, it's in group 6. It needs 2 electrons to be happy. Oxygen, pretty much always, is 2-. If I do crisscross, it tells me I've got Fe2O2. But that's nonsense, because you've got 2+ here, and you've got 2- here. You don't need to have any more either side in order to make the thing work. So actually, it's just FeO. It's another example where you have to be careful. Let's try another one. Copper 1 phosphate. I've got the 1 in brackets, so it means I have a positive charge. I've then got phosphate. It's another polyatomic we have to master. From my previous learning, I should know it's PO4, 3-. Now I can do my crisscross. So Cu will require 3. But PO4, I only need 1. So it's CO3, PO4. Done. Okay, let's do the final thing. Now the final thing we're going to go through is deducing the names from formulae. When you're deducing names, again, work out the formulae from the ions first. As an example, let's do Li2S. Now if I think of lithium, lithium's in group 1, so it is always going to do Li+. Now because the name doesn't change for metals, I'm just going to write lithium. But here we've got sulfur. Now because I've got 2 lots of 1+, that's going to be a 2+, which means sulfur is going to be 2-. So it's going to be lithium, and because it's become an ion, I have to add the ide suffix. So it'll be lithium, sulfide. Alright? Sulfur pretty much always is 2-. But there are some compounds where it has different charges, and that's complicated, and that you're going to cover a lot more in redox. But for our purposes here, we know it's going to be 2 minus because we know that lithium will always be 1 plus. Okay, let's try another example. CaNO3 2. Calcium's in group 2, so it has to be 2 plus. NO3 is a polyatomic. Now, from my previous understanding, I know that NO3 is going to be minus. This is quite nice actually, because even if you forget that small detail, you can kind of infer it from the formulae, because you know calcium's 2 plus, so it's going to be below 2 lows. So in order to make this whole thing balance and work, it has to be 2 lots of them. Okay. So, how do you name this? Well, calcium remains calcium. And now we just have to put the name of the ion. And the name is calcium nitrate. Remember, the 8 refers to the oxygen. That's in the polyatomic. Let's try another one. VO2. So for this one, this is vanadium. But I don't know what the charge is. As a transition metal, I know I'm going to have to put the charge in a bracket somewhere. I have to work out what that is. I've then got oxygen, but because it becomes an ion, it's going to be oxide. So the big challenge with transition metals is working out what's in here. So let's work it out. Oxygen is going to be O2 minus, but I've got 2 of them. So one of them will give me 2 negative charges. But with 2, I now have 2 lots of those 2 negative charges. So how am I going to get a charge on the vanadium side which balances those out? Well, I need to have the equal number for vanadium which are positive to counteract this negative, so it's going to have to be 4 plus. So those positives counteract those negatives. So what we have is vanadium 4 oxide. Okay? Super. Let's try one more. So here I've got titanium and I've got this polyatomic ion. So it's going to be titanium something and then the name of the polyatomic. Now in this case it's called hydrogen carbonate. But what's in there? Now let's break this down. HCO3 as an ion is just minus. Okay. But I've got 2 of them. So I've got 2 of these negative charges. I've only got 1 titanium. So in order to make this whole thing work, I need to have 1 lot of 2 plus. So the ion for titanium has to be 2 plus. To reflect that in the name, I need to use Roman numerals. I need the Roman numeral for the number 2, so it has to be 2. Okay. And that's how you do it. So in order to tie it up, I'm just going to do a quick multiple choice focus. I find multiple choice can really trip you up with these kind of questions. And by going through these answers, I want to kind of go through some techniques which I think will guarantee you good marks. So let's try a question, very straightforward. What compound is formed when beryllium reacts with chlorine? And there are your 4 options. Now you might see it straight away, and if you've done that, great. Even if you think you're on top of your game on this, I do think you need to write out your ions and just double check. Get your thinking down on paper. So as an example, beryllium is in group 2, so it has to be 2 plus. Chlorine is in group 7. So if it's in group 7, it needs 1 electron to be happy, so it's going to be Cl minus. I can really quickly do my crisscross, so it's going to be Be1 Cl2. Now let's have a look at the answer and see if this matches with anything. Can't be that. Be2Cl? No, can't be that. That looks good. And just to double check, no, can't be that. So by working it out properly, you can get to the answer and you guarantee the mark rather than sort of hedging your bets. Let's try another question. Metal X has only 1 oxidation number and forms a compound with the formula XPO4. Which formula is incorrect? Much trickier question here. And let's go through it. If it's got that formula, I need to work out the oxidation number first of all, which effectively is the same thing as the charge. So it's X something positive, and then I've got PO4. Now this is testing your knowledge of your polyatomics basically. PO4 is 3 minus. I've only got 1 of each, so in order to counteract that 3 minus, that has to be 3 plus. Okay, so it's X3 plus. Now let's have a look over here and see if this all works out. Now NO3, from previous learning, each one is just 1 minus. But I've got 3 of them. so it's 3 minus. I've only got one lot of X, which we've established over here is 3 plus. So that has to be 3 plus. So it works, that's good. Let's have a look at XF3. Fluorine always has a charge of just -1 because it's in group 7. I've got 3 of them, so that's 3 lots of negative. That's a good thing because in order to counteract it, X has to be 3 positive. So that one also works. Let's have a look at this one. Now I've got SO4. Now SO4 is 2 minus, but I've got 3 of them. So it's got to be 1, 2, 3, 4, 5, 6. In order for X to counteract that 6 negative, X is going to have to be 6 positive. I don't think that is right. So when it asks me which formula is incorrect, it's got to be this one. Okay. Now just for completionism, let's do this one as well. So I've got OH. From previous learning you should know that OH is OH minus, but I've got 3 of them, so it should be 1, 2, 3. In order to counteract that 3 negative, X has to be 3 positive. So again, that works. So you can see that the odd one out is XSO43. That's a tricky question where your knowledge of polyatomics is really put to the test. Let's try one more question. The formula of europium 4-phosphate is EU3PO44. What is the correct formula of europium carbonate? So, in order to work this out, this information here, you could use. And if we're just going to break this down, we know that europium has got a charge of 4 plus, and phosphate, in order to make this work, has to be 3 minus, okay? And you can see that by doing crisscross, you get the formula here, 3 lots of europium, 4 lots of phosphate. The question is, does it add up with all this one? Well, let's have a look. So which is the correct formula for europium carbonate? So first off, let's establish which formulae actually have carbonate. You could do a process of elimination here, or you can actually just work it out. Now europium is 4 plus. Carbonate is CO3 2 minus. If I do crisscross, let's work out what I've got. I'm going to have europium 2, but in terms of the carbonate, I need 4 of them. Okay? And as a result, that's your formula. But, do I need that many? Because your initial instinct would be, oh yeah, it works out with crisscross and you go straight there. But let's think about it again. Europium has a +4 charge. Carbonate has a 2 negative charge. So surely, in order to balance them out, I only need 1 more of these. In which case, this is incorrect. What I need, if we look over here, is 1 lot of europium, so I'll leave it, and 2 lots of carbonate. So that's your formula. So that we've worked out wrong. This is obviously wrong because 1 of each, we know that europium is 4 plus, and that's 2 minus, that's not going to work. This isn't even bloody carbonate, it's hydrogen carbonates, that's nonsense. So we're left with this, and it works. So by doing a process of elimination and by working out the problem, you can get to the correct answer. So I hope this has been helpful, this tutorial. Feel free to write down a comment at the bottom of this video if it has been, and good luck with the rest of solving questions on this.